If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things. That also really helps us out as well. Hi, welcome to another edition of Easy Theory. So we're ready to actually be able to convert a PDA to a CFG. So what we talked about before was that we modified the PDA so that we had these two properties, that there was only a single final state, and that actually three properties. Single final state, the stack ended empty and we forced it to be empty. And finally, every transition either pushes or pops onto the stack, or but it can't do both of those operations at the same time. And the consequence of that was we had a picture of the stack height over time in terms of the number of transitions that looks something like this. And one of the interesting things is that on the very first transition and the very last one, they have to be matching in that they have to involve the same character. This one pushes the special symbol, this one pops the special symbol. But in between, really anything can happen. But between every pair of these mountains right here, right at the start and the very end, those ones have to be matching also. And what we can think about is, if we look at the mountain in between those two, let's say these pink transitions, then we have a smaller version of the same problem. And we can model different size problems into in terms of other ones. So let's actually figure out, how do we do this? Well, what does a CFG need to have? It needs to have variables, terminals, rules, and all that stuff. So the start variable, remember, is all the strings that take us from the start state to the only final state, in this case, in the PDA. That's what the start variable of the grammar is supposed to do. So what is a generalized version of that same problem is to consider going from any state to any other state. This is what we do in mathematics and computer science. We have a problem we want to solve, which is going from let's say one state to another state, particularly the start state to the single final state. But let's generalize it and allow ourselves to be able to think of each of these subproblems in terms of another subproblem. So this is how we're going to set it up. So I'm going to have a bunch of variables right here, and they are going to be named A sub PQ, and this is just a variable name, but I'll tell you what it represents in a second, but it's just a variable name. So for each P and Q are states of the, I should say, modified PDA. So we have to do those changes to the PDA that we've talked about before first, before we proceed with this. But assuming that we actually did that, we're going to have a variable for each pair of states. And it could be that P is equal to Q. So a lot of students tell me, do they have to be different? And it turns out that they actually have to be the same sometimes. But yeah, so what is this? So we're allowed to have P equal to Q here. So the meaning of this, so A sub PQ supposedly will generate all strings going from P to Q with the same stack height. Okay, so that's what we're interpreting this to mean. So then it's pretty clear that the start variable here should be A sub Q0 going from the start state to, I'm going to call it F, the single final state. So Q0 is the only, not only, there's only one start state. Q0 is the start state, and F the single final state. Okay, uh, based on this reasoning right here. Now we haven't actually made the rules or anything, but assuming that we are able to do that, that's what the start variable will be. And that's why we insisted on a single final state, because we have a single start variable to deal with. So based on this, we need a single final state to arrive at. And we obviously have a single start state, so that's not an issue. Okay, so let's actually try to think of this in terms of problems that we want to solve. So because this is a recursive type problem, let's think about the base case and then the inductive case. So what would a base case of this be? So base case. Well, what is the smallest problem that we can have? Well, remember we have these mountains and we have the matching transitions at the bottom on both sides. So the smallest version of the problem is when we're at the very top of the mountain, we're at the peak. So that means that the state actually has to be the same. So if we have two transitions, say that look like this, so transition up, and then immediately we're going back down. And so this is the peak of some mountain right here. It may be a small mountain or a big one, it doesn't matter. So what we notice here is, right here is the end of one transition and the beginning of another transition. So because of that, we need to be able to handle, well, what happens when we're at, when we ended a transition and need to start another transition at the same place? Well, that involves a variable a sub p comma p. So the same state in both cases. Well, it could be in the PDA, let's just say the state p is here. It could be that there are a bunch of transitions that eventually come back to the exact same state. And it could be that this variable right here will generate a whole bunch of stuff. That's entirely possible. But one thing that we are absolutely certain that it can make is the empty string. Why is that? Well, what string can I take going from this state to itself without doing any transitions? Epsilon. We didn't actually read any string. So this is going from this state to this state without, in this case, not doing anything, because this situation doesn't have any transitions at all, because this is one transition, this is another one. I'm just looking at this one scenario right here, the base case. In fact, even involving these two transitions is an inductive case. So I don't know necessarily whether P is going to be ever a mountain right here. But I know at some point some state will be, because in order for this mountain to ever exist, there needs to be a state at this location, because a mountain always exists in any computation. So there's no reason not to include this for every single state. And in fact, this will always be true regardless, because going from a state to itself without doing anything is, because it has the exact same stack height too, if we don't take any transitions. So what we're going to do is, there are going to be three types of rules. This is a type 1 rule. Okay, in other textbooks put these in different orders, but again, there are always three types of rules. Okay, so that's the base case, and involving any transitions at all is going to be an inductive case. So let's look at an inductive case. Inductive case. So one case could be that we have some crazy looking mountain right here. And then immediately after, we have some other crazy looking mountain right here. Okay, so, and we're going to assume here that we have the exact same stack height at the bottom of at the two mountains right here. Well, let's see what happens. Well, let's say that we're in state P right here. Yeah, so this is a state P. And let's say that we want to go to a state Q way over here. So after traversing these two mountains, we end up at state Q. And the point at which it touches back down to Earth, it might not ever do this, but let's just assume that it does. I'm going to call that state R. Well, how can I get from P to Q on the same stack height? Well, one way is there could be many ways. One way is to go from state P to state R, because they have the same stack height, and from state R to state Q. So we can phrase this as, I want to go from P to Q, and one way to do that is read whatever it takes to get from P to R, whatever string we read to get from P to R, and then right after that, we read some more to get from R to Q. So whatever it takes us from P to R, concatenated with anything that takes us from R to Q. So we have, in fact, we can just read it off like this: A sub PR, A sub RQ. Because whatever this variable generates, I have no idea what it generates, nor this one, but I know that if I can get from P to R with the same stack height and from R to Q with the same stack height, then I can get from P to Q with the same stack height. And whatever each of these variables can make, I just read off whatever the first one can make, and then the second one, whatever it can make. If this variable, for example, doesn't generate anything, then this rule won't have any purpose, because if there's no way to get from P to R, then this route to get to Q is entirely useless, which is fine, because that was impossible in the PDA to start with. So because of that, we don't know necessarily which of these P, R's, and Q's are going to be placed wherever. So we're going to make this for every triple of states. Okay, so just like before, the P's, Q's, and R's can actually all be the same. That's entirely possible. So the thing is, these rules that we're making right here have absolutely nothing to do with the structure of the PDA, just the states themselves. So this is just basically saying, if I can get from P to R without changing the stack height, and R to Q without changing the stack height, I can get from P to Q without changing the stack height. Cool. All right. So obviously none of these, this and this type of rule, which actually we call type 2 rules. So this is a type 2 rule. Well, this of course has absolutely nothing to do with the transitions of the PDA. So now the third type is going to wrap everything up nicely for us by looking at the transitions. So the only other case, other possible inductive case, is where we have a single mountain. So if we have a single mountain, if we have two mountains, then type 2 applies. So now we just have a single mountain to deal with. And we're going to assume that it doesn't touch back to Earth, because if it touches back down to here, we're back in the type 2 situation. Because we must have two mountains in that case. So we have this situation, and we talked about before that because it doesn't touch back down to Earth down here, that the beginning and the very end transitions must involve the same symbol being pushed or popped on the stack. So this is, let's just say we're pushing an X. The X could actually be any character. It doesn't matter what it is. As long as the one at the end pops the exact same character. Okay. Well, they would have to, because it never comes back down to this yellow line. If it ever did come back to this yellow line, which is over here, it must pop that character because it's a stack. Okay, so how are we going to handle this here? So the way I teach it is I blow it up a little bit. So let's say that the push one is right here, and then the rest of the mountains in between. And we have the, let's make this have some room. So we have the ending one right here. So again, we are pushing an X on this guy, and we're popping that same character on the other side. Well, on this transition right here, I could be theoretically reading any character or not reading any character, right? So let's just say that we are reading an A. Well, the A could be epsilon. It's not actually a character necessarily. It's the whatever is being read or not read. And then if it is epsilon, we can just substitute it in later. But let's just assume that it's reading an A. And on this one, it could be totally independent. Let's just say we're reading a B. Again, it could be epsilon. It doesn't actually matter. Okay, so just like before, I'm going to call this, at this point, I'm in state P. In this one over here, I'm going to be in state Q. In this one, actually these two in the middle could be arbitrary. It could be anything really. So let's just say that the first one is state R and the one on the right is S. So how do we phrase this in terms of a recursive problem? Well, again, we're trying to get from state P to state Q. So again, the left variable of what I want to be able to generate is from P to Q. Well, how can I, of course, there could be many ways of getting from P to Q, but one way of doing it is we go on this transition right here, do whatever we take to read this, to get from R to S, and remember, note here that the stack height is identical right here. The stack height is identical. So, and then whatever it takes to get from R to S, and then we read whatever it takes to get from S to Q. Well, one way of getting from P to R is reading an A. So reading an A. Well, we have a meaning of what going from R to S actually is with the same stack height. That's the variable A sub RS, because that's going from state R to state S with the same stack height. And then to get from S to Q, we read B, whatever that transition says. Again, if either of these is epsilon, we just cross this off and just put nothing there. Okay, and when do we do this? We do this for all pairs of matching transitions. Again, if I have a transition that pushes something and another one that pops, it may or may not have something to do with the same stack height. But we are assuming by induction that we can get from R to S. So the inductive hypothesis is going to help us right here. Assuming we can get from R to S, then I can get from state P to Q if it's a matching transition. But if the choice that we make happens to not work, then either some other inductive case is going to fail or the base case is going to fail, at which point that computation won't work. But that's okay, because PDAs and context-free grammars are non-deterministic. So it will make the correct choice if there in fact is one. And as you might expect, these rules are called type 3 rules. Okay, so just to recap, so type 1 rules are going to be every state P, so all the states in the PDA. If there are 10 states, I'm going to make 10 rules with this. Then I will make all triples of states right here. So if I have 10 states, this would make 1,000 rules, because it's 10 choices for P, 10 choices for Q, 10 choices for R. Then once we go down here, this will depend on the number of matching transitions. If it ends up being 10,000 rules, that's totally possible. It might be 0 in the case that there are no transitions at all. which is totally possible, by the way. Okay, and so that is the conversion from a PDA to a CFG. We have to make sure that the PDA has the right form in that it has one final state. Every transition either pushes or pops so that we get this stack height changing, always changing height behavior. And we also, so those are the changes we have to make. And the stack has to end empty because that'll allow us to match the first and the last transition. And then what we did here was we made a whole bunch of rules that is basically just just basically a recursion problem, because it's just looking at base cases and inductive cases. The base case is when you're at the top of a mountain, and the inductive cases are either you have multiple mountains, in which case you split them up into individual mountains, and once you have an individual mountain, you look at the beginning and the end transition of the mountain, and then you recurse up the mountain, so to speak. So that's literally all it is. It's making use of the recursive structure in these in the computation here, which are these mountains. So hopefully that was interesting. If this was difficult for you, that's totally okay. Please put your questions down in the comments. I read all of them. As always, please like and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, I'll see you next time.